All right, everyone. I'm Cassandra Sparks from MIT Lincoln Laboratory. I'm starting the first of 3 talks today about security in Accumulo. And there have already been a lot of really good talks about how Accumulo is used, and in particular, how important visibility labels are to Accumulo and how central security is to the way Accumulo is designed. And what we're looking at here is a different view of security and a different threat model against an Accumulo database. And so in particular, today I'll be talking about the work that we've been doing on coming up with verifiable results to Accumulo queries using cryptographic techniques. So I'll talk a little bit about what our threat model is, and then go into detail about the cryptographic techniques we're using. So don't worry, you don't have to be a cryptographer to understand this talk. I'll explain all the primitives that we're using here, and go into some more detail about some of the design decisions that we had to make to fit this into Accumulo, and the specific code that we're running. So we have code written for this that we're working on an open source release for. So before I get into any of the technical details, I just want to talk a little bit about MIT Lincoln Laboratory. So we're a Department of Defense funded, federally funded research and development center associated with the Massachusetts Institute of Technology. So they have, this center of great research excellence, and we're a branch of that deals with this military funding situation. So our goal overall is technology in support of national security, and there's a lot of different mission areas that deal with this. I won't get into detail about all of these right now, but the one in particular that I want to focus on is the cybersecurity and information sciences area. So this is the area that is particularly interested in and focusing on securing things such as Accumulo. And the reason this is relevant to us is because there's this big government common big data architecture that we have that Accumulo is at the center of. So right now I'm going to talk about cryptographically securing Accumulo because it's at the center of all of this stuff, and if it's a common point of failure, then that would be really bad for us. Later on in the day, I think at the end of today's talks, there will be another group from Lincoln who is talking about the analytics side of things, so doing analytics on data that's being stored in Accumulo. But for now, I'm going to focus on cryptographically securing it. So there's a lot of different threats to Accumulo that we can think of, and here's 4 examples here. So you can imagine if you're outsourcing a cloud server running Accumulo to something like Amazon, you might be worried about them peeking in on your data, or you might be worried about someone fabricating data that's malicious and misattributing that to a legitimate client of the server. You can also imagine a malicious insider. So this would be someone such as a system administrator who has access to your Accumulo server, who could try to learn data that they're not supposed to learn, or change the data in the server and misinform the legitimate users of the server. And that's specifically what I'm going to focus on today. There's also, you can think of malicious clients. So if the server is legitimate, but there's a client or several clients who are trying to misuse it somehow and try to learn data that they don't have access to, or perhaps learn about other clients' queries. So this is specifically the threat model that the existing infrastructure in Accumulo of visibility fields focuses on, because it trusts the Accumulo server not to return results that clients shouldn't have access to. You can also imagine an external attacker. So someone who doesn't have legitimate access to the server, but tries to hack into it and gain access to it. We aren't designing things that would detect that in particular, but if they do manage to compromise some of the hardware in the system or get an admin account on the system, we would be resilient to that kind of threat. So like I said before, we're focusing on the malicious server side of things. So what if we do have this outsourced cloud situation, or what if we do have a malicious system administrator, or some of the hardware that Accumulo is actually running on is compromised in some way? So just a high-level overview of what the Accumulo situation looks like. So we have clients over on the left. They're connected to Accumulo over some network, and then Accumulo and some of its associated infrastructure. Like I said, this is a high-level view. So we have Zookeeper up here, and then it's running on the Hadoop distributed file system over on the right. And you can imagine there's system administrators associated with all of these areas. And we can look at what happens when any of these sysadmins is corrupted or malicious, and what protections currently exist and what protections we're trying to add to Accumulo. So if the HDFS admin or HDFS server is corrupted, then there's already a solution in place here where Accumulo can do data at rest encryption from the Accumulo down to the file system level and protect your data from that threat. So we're not focusing on that because there's already a solution in place. Similarly, if the network is corrupted, there's also ways to protect your data that's being transmitted over the network to Accumulo with TLS encryption, so we're not worried about that. But that leaves the Accumulo and Zookeeper admins, and I'm going to focus specifically just on the Accumulo admin for the rest of the talk. But there's no integral safeguards in Accumulo already for this kind of threat. So this is specifically what we're focusing on, is cryptography that protects against these specific levels of administrator. And we have several solutions in place that we're working on or have already accomplished that protect against this. So we're using cryptography to improve the security of Accumulo, and one of the ways is with end-to-end signatures, so using digital signatures on each cell of data that's inserted into Accumulo. Another is with fully verifiable query results. We're also looking at using encryption at the cell level of Accumulo, so we have ways of encrypting different fields in each Accumulo cell in different ways, so you can still use Accumulo, but you get protection, confidentiality protection in particular, against the system administrator. And also attribute-based access control, where we're actually cryptographically enforcing Accumulo's visibility labels. So even if the server tries to maliciously return data they shouldn't return, you still get confidentiality guarantees in that situation. So I've been using this word confidentiality here, and specifically there's two different kinds of guarantees that we're looking at providing. One is confidentiality, which is the protection of the specific contents of your data against someone who doesn't have permission to read it. And the other one is integrity, which is the focus of this talk, which is protecting the actual contents of the data from being changed or added to or deleted from in some way. So that's what I'm going to focus on for the rest of the talk, and in fact I'll go into more detail about these two solutions on the left, the end-to-end signatures and the verifiable query results. So first I'll talk a little bit about the end-to-end signatures. And so there's several components to this. I'll talk about how digital signatures work for those of you who aren't familiar with them. And I'll also go into some detail about the design decisions that we had to make in our code on how to fit this into Accumulo's existing structure, and the actual some technical details about the code that we have and the implementation that we've already come up with. So let's go into how inserts currently work in Accumulo. So right now the situation is relatively straightforward. So you have a client who wants to insert some data into an Accumulo server. Let's say for the sake of the rest of this talk that we're a medical company and we're using Accumulo to store all of the patient's records. So you might have a patient with at some hospital with some diagnoses that you're storing in the database, and this is only viewable to doctors. So maybe one doctor writes this information out to the database, and another doctor that they've referred their patient to wants to read it back. Right now, there's no mechanism in place for this second doctor to guarantee or to have any level of cryptographic confidence that this is the actual data that the first doctor meant to write out to the server. So if they don't trust the server, if the server is not trustable, if there's someone, say, running it with an agenda perhaps, then the second doctor might worry that the diagnoses here are an incomplete list, and they have no idea whether this data has been changed in transit or not. So what we're looking at is cryptographic mechanisms to enforce security in Accumulo, and as it turns out, there's already a cryptographic solution to this that works really well called digital signatures. And so a digital signature algorithm has three components. The first component is with key generation. So this is to create this, the private signing key and the public verification key that the clients will then use to put these guarantees on the data. I'll go into that in just a second. And so the second step is to actually sign data to compute the digital signature. So this takes the message that's being signed and the private signing key. So I'm emphasizing that it's private because only the client who's signing things with this key, these are strongly tied to the client's identities, should have access to this key. And with that key and the message, you can compute a signature of that message. And the goal of this is to tie that message to this specific signature with the private signing key using the paired public key. And so the way that works is with verification, where you take the message, a signature, and a public verification key, and you check to see if the message and the signature correspond to each other under the specific identity that signed it. And so if they did, that's great. Everything will check out. And if they didn't, if you put in the wrong message or some wrong data here, it will be able to detect that. So the security property here that we care about is that you can't forge a signature of data without already knowing the private signing key. So in particular, if a client signs data and writes that to Accumulo, then another client gets that data out and verifies the signature, they know that the malicious server couldn't have modified that data in transit, that this is data that was actually signed by the original inserting client, in our case, the treating physician. So if you look at how this works in Accumulo, just the general workflow of this, you start out with the same data that you were going to insert anyway, and then before writing it out to Accumulo, you take your private signing key and compute a signature of this entry into Accumulo, and you include that with the data that you're writing out to the server somehow. And I'll go into more detail about how this can be done later. Then all of that gets written out to the database so that when the querying client fetches it back, they can also fetch the public verification key from the inserting client and use that to verify the authenticity of the message. And so we add this extra procedure here to give the querying client confidence that this is actually a message that the inserting client intended for them to receive. So we've implemented this code in Python already, and so we have this running in Accumulo, and it uses the PyAccumulo library for interfacing. And the advantage here to this approach is that there's no server-side modification needed. So this is good partly because we don't trust the server in our threat model anyway, so we have to be careful when we are modifying anything that the server does. But it's also good because any version of Accumulo that PyAccumulo supports, the version of PyAccumulo that we're using, this will also support. So it gets backwards compatibility to some extent. And we're also in the process of open sourcing this. So there was just a panel about open sourcing things from the government. We're still working on that. But if you want to know when this is released to the community as a whole, you can email us at pace-contact@ll.mit.edu, and we'll let you know when this is actually released. So when we were writing this code, there were several interesting design choices that we had to make. So one of them was where exactly to store the signature metadata that we're computing, and another one was which of the different signature algorithms out there do we want to use. And so I'm going to go into some detail about both of these right now. So first of all, let's talk about storing signature metadata. So obviously the best of all possible worlds would be if there was already a signature field in Accumulo that we could use. Like I said before though, we aren't changing anything about Accumulo yet. So we want to figure out how we as a client can add the signature to the entries that we're inserting into Accumulo without this dedicated field. So there's 3 different approaches that we've come up with. One of them is to just store things in a completely separate table. So you have, say, your original patient records that you're going to store, and that table is completely untouched. But you're creating a separate table now that has all of the signature metadata in it so that when you fetch the original cell, you can also fetch the signature of that cell. The advantage here is that you're not changing anything that you're inserting. So everything that would normally be in the unsigned table is now going to be in the signed table. But the downside here is that now you're doing twice as many queries and twice as many writes. So every time you want to write something, you have to write it, and you also have to write a cell that contains its signature. And if you want to query something and verify it, you have to query that cell, and then you also have to query for its signature. So that might or might not work for you. If it does, great. If not, we have a couple other options. So the second option is to store things in the value field. This kind of makes sense because the value field is meant to store unstructured user data, and this is exactly semi-structured user data. The downside here is that this might interfere with iterators you have running. So if you have a lot of, like an iterator heavy workload that does a lot of computations on the values stored in Accumulo, this might not work for you, or you might have to go through and modify all those iterators to be aware of the extra structure of the metadata stored here. So again, if that works for you, great. If not, we can also store things in the visibility field. And so this solution just involves ORing things to the end of it. You might think that's a little bit worrying from a security perspective, because now you're adding something, adding a way for a user to have access to this. But this isn't actually a concern, because what we're adding here is essentially random from the user's perspective. So anyone who could a priori forge the visibility for data that they aren't supposed to be able to see anyway could also just forge the signature of that data in the first place, so they have to have access to the private signing key anyway. So we're not too worried about that. The advantage here is that you're not storing anything in the value field, so it doesn't interfere with iterators. But the downside is that Accumulo has a lot of optimizations in place already to make sure that visibility field evaluation goes very quickly. And this can interfere with some of them, right? Because like I said before, this is adding something essentially random to the end of the visibility field. So Accumulo's fast fail operations that evaluate this won't be able to cache things as well, or at all, because everything will be different, because everything will have a different signature. So again, none of these is strictly better or worse than the other, and this really depends on your use case. So we support all three of these options, so that whoever's implementing this in their code can determine what works best for their specific scenario. Sure.
But I just want to make sure, you said you add on to it, but you're not replacing.
Right, we're not replacing the visibility field. So the way it works is that you have the old visibility field, and we just OR this onto the end of it. So you have to have access previously, or you have to have this random unassigned visibility label, which no one will have. Okay. So moving on from that, we also have a choice between different signature algorithms. So in fact, we're looking at three different choices here. The first one is to use RSA signatures. The advantage of these, so I won't go into detail about how the algorithms work exactly, but I will say that these are geared towards fast signature verification. So they're not so fast to actually come up with the signatures, but the idea is that you come up with the signature once and you verify it many times. And so it's optimized towards that. Unfortunately, they also have a very large signature and key size, so you have to keep track of a lot more data when you're using these signatures. We also provide what's called elliptic curve signatures, the ECDSA algorithm for future reference. And these are much faster to create signatures than the RSA signatures are, and they are also much smaller, so you have to keep track of less data when you're using these. We provide both of these options, and a third option is to use what's called message authentication codes. These are a symmetric key algorithm, so they're not quite the public key signatures that I described earlier, but they're much faster than the other two options that we have here. And so they're several orders of magnitude faster at least. The one disadvantage, though, is that if you have one malicious client, the range of the damage they can do to the integrity of the database is much, much wider than if you're using just public key signatures. So right now we support RSA and ECDSA signatures, and we're looking at ways to use these message authentication codes that can retain some of like similar security guarantees to the public key version, so we can't just have one client that's tromping all over the database. And we have also benchmarked these. So before you look at these numbers and gasp, these are on a single node virtualized Accumulo instance. Partly because it was faster. We're doing this in a rapid prototyping type of way. So it was faster to get these benchmarks, but also the server's performance isn't what we're looking at here in particular. So what we're looking at is the performance of the signature algorithms, which, like I said before, are all happening client side. So as you can see here, there's a fair amount of a performance hit going on, where there's about 1 to 2 orders of magnitude more time taken to sign things and to verify things than there would be in our baseline case. We're aware of that, and that's one of the reasons we're looking into message authentication codes. And the rest of the talk that I'll be presenting is also much faster than this solution. So just to sum up how signatures work, so these allow clients to verify parts of data integrity where the server can't modify or fabricate results, but I kind of elided one security thing that they're missing, which is that they don't detect if servers omitted a result entirely. And so you can see how a server can just omit a cell completely and not let a client know about its existence, and you can't sign the lack of an entry in a certain place. So in other words, so it supports, or it can detect modification and insertion, but not omission of data. In the rest of the talk, I'll talk about a technology called authenticated data structures that does support all three of these security properties that we'd like to have. And it's also much faster. So I'll go over just what these are at a high level, and I have two examples of authenticated data structures that we've investigated for using in Accumulo. So overall, authenticated data structures, or ADSs, are data structures that allow provably correct query results. Where correct here is defined where an inserting client comes up with a representation of the data set, and querying clients can compare their results to that representation of the entire data set. And in particular, these work on range queries, which is great for Accumulo because we heavily support range queries. So the model for this is that there's an inserting client and a querying client that are communicating both with each other and with this malicious Accumulo server. And to start out with, the inserting client computes an authenticated data structure. From this ADS, they can also compute a digest that acts as a small, constant size relative to the size of the entire data set, representation of the entire data set. So this is the data that the client can then use to verify the results of the query. They then write the ADS out to the Accumulo server. So this is what the server will use to compute the query results now. And then a querying client who can do a query, and they fetch back not just the results of that query, but what's called a verification object that contains both the results and some metadata about the results to let them recompute the digest and verify that this result was actually correct. So they send that to the querying client. The querying client can then fetch the digest of the data set and verify that it's correct. So then if the verification object was falsely computed by a malicious server, they then send that over to the querying client, and the client can detect, similar to with signatures, that this is in fact the wrong query and should not be trusted. So one example of Merkle of an authenticated data structure is what's called a Merkle hash tree. And so these are, I think, a good example of just how these work overall. So the way you compute a Merkle hash tree, I'll just go over their computation and how a range query is actually performed on them. So you start out with a list of data that you're storing. So I'm just going to use the even numbers from 2 to 16 because it's a small example. And the first step is you're going to compute the tree bottom up. So you start from the leaves, and you compute the hash value of each of these elements. So in particular, the hash function that we're using here is a cryptographic hash function that has the property that given a hash function or a hash value, you can't compute two elements that hash to the same value. So with this cryptographic hash function, you hash all of the node element or the leaf elements here in the leaves, and then for each internal node, this is going to be a binary tree. So each internal node stores the hash value of the concatenation of the values stored as two children. And then we just iterate this process up to the root of the tree until we get this root hash value here. Now know that the root hash value depends, however indirectly, on all of the elements actually being stored in the tree. So this is what we can use as the digest of the authenticated data structure. So this is the value that the client will then compare against to make sure that their query is actually correct. When performing a range query over this data, say we want to catch the range from 5 to 9. So the correct result for this is, of course, 6 and 8. But the question here isn't just what the result of the query is, because Accumulo can tell you that regardless, but what extra metadata we need to include with the query result in order for the client to verify the root value. So intuitively, we can think of this as needing to provide enough information to recompute that root hash value. So if we just traverse up the tree kind of naively, we can say, well, what extra information do we need just from the query results to recompute the root? So we can compute the hash values of the elements that we already received. They're siblings of the same node, so we can also compute that node's hash value. But we don't know its sibling's hash value, so that has to be returned as some extra metadata as part of the verification object. We can now compute their parent, and we have to do the same thing again. So the right sibling of the root isn't known, so we have to return that also as part of the verification object, so that I can now blank out the screen by accident, so that we can now compute the root of the tree. So this works for some query correctness properties, but not all of them. So in particular, this naive solution here allows a server to omit elements from the edges of queries. So if an element was returned or was not returned from the middle of it, the verifying client could be able to tell from the structure of the verification object, but we can't tell from the edges of the query itself. So in other words, we don't get either of these nice omission properties that we would like in signatures, and we do get one of them, but not both of them with these naive with these naive Merkle trees in particular. So the solution to this is to now return not just the range itself, but also include the boundaries of that range as part of the verification object. So now if we have the same tree and the same query over it, we need to return not just 6 and 8, but also 4 and 10. So that way, when the client gets the data back, they can also check to make sure that the lower range and the upper range are adjacent to each other so that nothing was omitted in the entire structure of the tree. So then we can go through the same process as before and see what we can compute from what we already have and what extra information we need to be able to compute the root hash value. So here we just need kind of the fringe of the tree here. We can go up a level and we just need this rightmost element. We can compute both children now of the root and compute the root itself. So now this is the process that the client would go through at a high level to compute the root value. They would then fetch the signed root hash value from the inserting client and compare those to each other. So if they're equal, they know they got the correct data from the server, and if they're not equal, they know that something went wrong somewhere. So to sum up the security of ADSs, we have, so naive Merkle trees can detect omission within the range, but not on the boundaries, and Merkle trees in general can detect any omission from within the range at all. So that's really great for Merkle trees to be able to do. On the downside, they're mostly used for static data. And so in order to get more dynamic data, there needs to be some kind of balanced tree-like structure. Because, when you try to insert something into an unbalanced tree, there's kind of two approaches you can take. The first one is to try to do an unbalanced insert, where you have some tree, and maybe you get really unlucky, and every element you insert just goes into kind of the left half of it, and eventually you get linear time operations for everything. So that's really bad. You could also just try reconstructing the tree every time you insert something to it, and of course that will also give you linear time inserts, which we want to avoid, right? So we want to maintain Accumulo's high ingest rate with these structures and not have a high security overhead. And so the solution that we have for this is to use a data structure called authenticated skip lists. If you've never heard of a skip list, it's a expected balanced tree-like data structure that instead of using kind of a heavy-handed invariant like red-black trees or 2-3 trees, it uses randomness to guarantee that in all but the most rare cases, you will get a logarithmic time insertion, lookup, and verification for these data sets. And so the reason we chose skip lists is because they're simpler to implement and they have empirically better runtime than any of these other balanced tree data structures that I mentioned earlier. So just to sum up, we have some additional work that we're doing that I mentioned earlier in the talk. So we're also looking at confidentiality to hide data from the malicious server and from unauthorized users. So we have per cell encryption that lets users flexibly encrypt different parts of the cell as they need to. And we're also looking at cryptographically enforcing Accumulo's visibility labels using both interesting crypto and key management techniques. We also, like I said earlier, we're looking at using message authentication codes, in particular hash-based message authentication codes, or HMACs, to get more security out of the signatures code, or more performance out of the signatures code, and trying to see how much security we can maintain with that approach. And we're also looking at using key management here to unify all of the components so that the client also doesn't have to worry about that. So just to wrap up, we have these signatures for data tampering detection. We're working on open sourcing this code that we have, and if you email us, we can let you know when that's available publicly. And we're also working on authenticated data structures. So if any of this sounds interesting to you, or if any of the stuff in the talk later on in the day is interesting, and you want to work at Accumulo or work at MIT Lincoln Lab on any of this, or do a rotation here, please feel free to come up and talk to one of us after this talk. There's a lot of us here today, and we have business cards that we can hand out and contact info that we can hand out as well. And with that, I'm willing to take any questions. Thank you. Right, so yeah, so those are both good questions for those of you who couldn't hear. So the question is, how do we communicate the digest value from the inserting client to the querying clients? And then also, how does the inserting client manage the digests that they compute along the way? To answer the first question, we're looking, so this is a public value. It doesn't need to be kept secret. So they can communicate that along to the querying clients however they want. As part of the key management infrastructure, we're also looking at just having an honest infrastructure for communicating those and keys so that the server can't perform, say, versioning attacks on the data. And so there does need to be some trusted way of getting that data transmitted over to the clients, and we are looking at that as well. To answer your question about the digests, so we have, there's kind of two different ways to do this. One is depending on what level you're computing the trees at, it might be feasible for the inserting client to keep track of all the data. If it's not feasible for the inserting client to just keep this authenticated data structure around and update it whenever they insert stuff, they can also do one query before they start an insert on the range of elements that they're inserting data over, and then get a fragment of a Merkle tree or a skip list back, and then insert elements into that fragment locally, so they only have to store a part of the data at any given point in time. And so that way they just keep the most recent digest, and then they can perform the query, verify the query, and then update that and publish the new digest that was a result of that computation. Does that answer your question? Yep. Great. Yeah.
So you characterize the performance on the client side of doing the cryptographic signatures. Mm-hmm. Assuming that you can solve that, 100x or whatever it was hit, have you characterized, given your approaches for putting the signatures into Accumulo along with the regular data, your three different approaches, like a different table or with visibility, et cetera, you characterize the performance characteristics and trade-offs of those three approaches?
We've looked at this very briefly, and so I mentioned that this will interfere with the fast-fail capabilities of visibility field evaluation if you're storing data there. Some early numbers that I ran suggested there's about a 10% performance hit with those, depending on the type of data, right? So if everything should evaluate correctly, then it's going to be less of a performance hit. If it's a very heterogeneous table, then it will be more of a performance hit. But we need to look more into benchmarking those. So you're right, we need to characterize the performance over on the server side as well. So not yet, but when we have more numbers and we get those released to the public, we'll put them we'll put them somewhere. If you email us, we'll send them to you. All right, I think I'm about out of time, so if you have any other questions, feel free to find me offline. Thank you. Or I'll find you.